Hello, everybody. Let us start our discussion today. In the last lecture, we left at a point where we realized that the ether hypothesis failed. We could not find the existence, or Michelson and Morley could not find the existence of a medium with respect to which they could measure the speed of the earth. And because of that, the Maxwell's equations, the Maxwell's electromagnetic theories, and the wave theory of light remained inconsistent with the Galilean transformation. The Galilean transformation demanded that the speed of light will change, and if you assume ether hypothesis with that, you should be able to measure the speed of light with respect to the ether. But Michelson and Morley failed to use that hypothesis to measure the motion of earth with respect to ether, which essentially meant that ether doesn't exist. And if ether doesn't exist, then you have to somehow find out a way of either changing the speed of light at different medium or not change it at all. If you don't change it, then obviously Galilean transformation expect that any speed will change if you go to a different inertial reference frame. That will not be respected. So there was this crisis in the physics that remained after Michelson-Morley experiment. And in 1905, it was Albert Einstein who came and resolved this puzzle. He realized that we were doing some mistake with the ether hypothesis. In the ether hypothesis, we said there is a preferred medium, which is the medium ether. So let me write the ether hypothesis a little bit different way now. A preferred medium we called it ether. With respect to this, speed of light is roughly 3 into 10 to the 8 meter per second. And Michelson-Morley experiment showed, let me say showed, doesn't work. So what is troublesome here is the fact that you are talking about a preferred medium. There is a particular medium in which the speed of light has a certain value. And that is not very comforting when you are trying to do physics, because you expect there is no such preferred reference frame. You want all the reference frames to be similar. Otherwise, who knows? Your preference may be different from my preference. Science is supposed to be more democratic. So Einstein came up with the following postulates. And let me write down the postulates, and I will read a part of the paper in 1905 by Einstein, which describes these postulates. Because these are, if you wish, the cornerstone of modern physics. It has not only given rise to a small thing like special relativity, but a lot of other things followed just from these two postulates. And this solved, obviously, the problem, the crisis in physics that we talked about, and we will see how. So let me first write down the postulates of special relativity. From now on, in our discussion in relativity, if something seems strange to you, that is just because your common sense is made up from some wrong ideas or not so legitimate ideas. So I will request from now on to pay attention on the logic on which things are being developed and forget about, if anything, that you have heard or learned on special relativity before, because that may be harmful for both of us. Okay, so let me write down the postulates. The postulates are just postulates. You assume them to be true and then you try to figure out consequences. That's how science works. If you figure out what you find out, what you work out using the postulates matches with the reality, what you observe in nature, then you are happy. You say, okay, so it's a good postulate, good theory, I will keep it. And that's how special relativity have been for last 115 years. There's no flaw which has been found in this theory. But if you find for some case the postulates doesn't work, you have to throw it out. Okay, just like the ether postulate does not work, we had to throw it out. So what are these postulates? First postulate is the democratic postulate, so to say. Physical laws are same in all inertial reference frames. And you see that I still only talk about inertial reference frames. And because this theory works only on inertial reference frames, it's called spatial relativity. So its special thing about it is that it only works in the inertial reference frames. And there is a general theory of relativity which works in all reference frames, but it's too complicated for us to learn it here. That's the first postulate, which is the democratic postulate, which says that whatever inertial reference frame we use, I'll write down the same physical law, which is very nice because that is what you want. Otherwise, everybody else can say my physical law is this, and another person say my physical law is this, and you keep on quarreling with each other. You never settle. That's not good. So this settles all those quarrels. But the second postulate is more drastic, and this may sound completely wrong to you at this moment, but believe me, it works. It does not depend on the speed of the observer or the source. And that's a big statement because so far all the velocities that we know of depends on the speed of the observer of the source. This essentially is telling you that the speed of light does not depend on which reference frame you are using to measure the speed of light. In all reference frame, the speed of light has a constant value. And this value, which we call c, is this. Because it's so sacrosanct a constant, we have considered these values to be the speed of light, to be more precise. So there is no error in this value. This is the value for the speed of light. Okay. So let me put a box around it. Now these are the two golden postulates of special relativity. Let me read a little bit from where this came for the first time, Einstein's paper in 1905, because it's interesting how he writes, how he puts in these two postulates. Example of this short, which obviously comes after one paragraph which I'm not reading for you. So that paragraph gives you the example. Together with the unsuccessful attempt to detect the motion of the earth relative to the light medium, this is essentially that light medium is the ether medium, and he's talking about Michelson-Morley experiment, and there were actually other experiments also, lead to the conjecture that not only the phenomena of mechanics but also these electrodynamics have no properties that corresponds to the concept of absolute rest. So you, when talk about mechanics of or electrodynamics, you cannot evoke a reference frame like the ether frame, where you say with respect to this frame, this is a special frame of absolute rest. With respect to this frame, we'll measure all the velocities, like for the velocity of the light. That is not to be the case. Rather, the same law of electrodynamics and optics will be valid for all coordinate system in which the equation of mechanics hold, as has already been shown for quantities of the first order. This essentially means in which the reference frames are inertial. So a modern way of putting it is that all physical laws are supposed to be same in all inertial reference frames. We shall raise this conjecture. So when you propose this, it's initially it's called a conjecture, and then when you propose it a little bit more boldly, you call it a postulate. To the status of a postulate, we shall raise this conjecture to the status of a postulate and shall also introduce another postulate, which is only seemingly impossible with it, namely that light always propagates in empty space with a definite velocity that is independent of the state of the motion of the emitting body. These two postulates suffices for the attainment of a simple and consistent electrodynamics of moving bodies based on Maxwell's theory for bodies at rest. Okay, so I'll stop reading from Einstein's work here. Essentially, at that time, the only force that people could unify was the electrodynamics, and that is the physical theory he is talking about. Now we know that these postulates holds for any other physical theories. So these are the two postulates. Now we'll see the consequence of these postulates today, starting from today. One thing that can be very clear to you, that the speed of light, it's a speed or a velocity, if you give it a direction, it's supposed to remain constant in all reference frames, and Galilean transformation tells you how this velocity or the speed changes across reference frame, which you have seen 2 lectures back. Essentially, is knocking at your door saying that the Galilean transformations doesn't hold anymore. So that we will see mostly in the next lecture, how the Galilean transformation has to be modified. But before we go there, for our sake of understanding, the topics of special relativity, we need to evoke what we mean by a reference frame. How do we do measurements in reference frames? These questions are very important, becomes very important when you come to special relativity. Because we do not ask these questions often, we start creating confusion around the theory of special relativity. So the way we will develop it logically is very slowly, step by step. And the first question we'll ask is, how do we make a measurement and how do you make a reference frame? Okay, so let's move out of this postulate for the time being. We'll come back to it at the end of today's lecture and see what consequence it gives us. So, making of a reference frame. And when I say reference frame, everything I talk about are inertial reference frames. Keep that in mind. I'll not call it inertial or write it down explicitly because that's the only type of reference frame we deal with here. So what do I mean by making of a reference frame? In mechanics, there are two things that we measure. We measure position, which is given by space, and we measure time. So these are our all measurements that we do are these two. For space, I have to measure three numbers. And we have learned Cartesian coordinate systems, which is the easiest one, where I need to tell you x and y and z position of this. And for the time, I need to tell only one position, one thing, which is what my clock reads at that given time. These two things are often measured together. You ask the question, where I was born, where was where and when. Okay, for me it was a long time ago. For you, it is not so much long ago. But that is a kind of question we ask. So this happens at a particular position in space, which is given by x, y, z, and at a particular time, which I call say t. And so these are the four quantities that I need to specify my birth. And this thing, which requires four quantities to specify, we'll call it an event. So event has both the information of the time and the space. Okay. So four numbers. But you see, there is a little bit difficulty because these numbers has a dimension of length and time doesn't have dimension of length. But we can be clever. We say, okay, time doesn't have dimension of length, but there is something we know is a constant of nature, which is the speed of light. Why don't we multiply this by the speed of light? So this also becomes the dimension of length. So I call the one coordinate as ct, the other coordinates as x, y, and z. And when I specify all these four coordinates, I specify an event happening somewhere in space at a given time. So what are the examples of events? Like, for example, I throw a ball up. So when I throw, the ball leaves my hand. That's an event that's happening at the position of my hand at a given time. Then the ball goes up and then it start to come down. It goes up to a certain height. So where it momentarily stops, so that's a position, happens at a given time. That's another event. Comes back to my hand, position of my hand at a given time. That's another event. My birth is an event. You may wish I will die soon. That's an event. This, when I am speaking to you, I am going through many different events. So these are events. And one need to measure these events. For example, if I ask you, what is the velocity? So let's say that I want to do a measurement. Question I am asking is, what is the velocity of some person? Let me call him Flash. What is the velocity of Flash? So how do I measure the velocity of Flash? I measure his position x1, y1, z1 at a time, at a given time ct1, and then at a different time I measure his positions again, and from these two you know very well how to figure out its velocity, his velocity. The question I am asking today is how these measurements are done. Okay. Now you may think that there is one person who has a clock because he has to measure the time, and he has a tape measure, scale or a long tape. He's going around and measuring different moment of where flash is at different moments, t1 and t2 at different positions, x1, y1, z1, and x2, y2, z2. But that actually is not possible. You are thinking of a person who may not be as fast as Flash. So how to do it? How to do the measurements? Well, there are many different ways, and what we will discuss today is a simpler way, which is easy to understand. So I will cater to that particular way of measurement. Now, when I say measurement, it's essentially a process, and every process requires a certain procedures to be followed. So here I am writing down the procedures of measurement. Okay, and we will learn by doing this how to constitute a reference frame. Okay, now first we will do a simplification. The simplification is that we'll consider one dimensional space only. And we'll label it as x. It can be done in 3 dimensions, just will increase the complexity. And I will try to draw certain figures which also I will not be able to draw properly. That's why we'll deal with only one dimension. If you understand one dimension well, then also you will understand any number of dimensions and 3-dimensional space easily. Okay. So when I say that the position of Flash, I will not talk about both all three x1, y1, z1. I'll only talk about x for this position. So here one event essentially is ct and x. So this two gives you one event, and we want to know how to measure many different events. Okay, so let's go through the procedure. The first what I do is I appoint many observers, and what I'm doing by doing this is defining a reference frame. One observer for each x. So you can imagine that there will be essentially infinite number of observers. But this is some hypothetical construction where we are assuming that I have called up one observer for each position in x. Okay. So what happens is they come in this room. There is a room which for the time being, I assume that they're all at the same place. So they come in this room. So let me draw 5 of them just for. And there is a special one. We'll see why I want one to be special. There is nothing special about him, but just I want to distinguish. Okay. They are given papers. They are given two things. One is a paper with a number written on top. So you get a paper as you volunteer to be one of these observers, and you are given a paper with a number written in top. So maybe this person get a paper, and the number written here is -1. Everybody got a paper. There no two people got the same number. That is important. That we'll see why it is important a little later. It's okay. And the other thing they got is a clock, and all the clocks are good and synchronized. Okay. So let me now, this person got another paper. It's written -2 over there, say. This person got another paper written +1, +2, and I could have drawn infinite number of people. Would have taken infinite time, so I don't do that. And this person got a paper which is written 0. It's nothing different, it's also a number. And you imagine that there are many others in either direction, and there are people in between 0 and -1 and 0 and +1 also, but I am not drawing all of them. Okay, so this is all they have got. They also got clocks. So let me just, so this is old fashioned clock with two hands, one hand a little bigger than the other. Okay, and all of the clocks are synchronized. So this is the first two steps. In the third step, what they do is the observers, so these people are called observers, go to x positions same as the number written in their paper. Okay. So the person who got 0 goes to the position 0, 1 goes to the position 1, 2 goes to the position 2, etc. So let's see what happens. So if I draw x this way, so this is x, so x varies this way. So let's say this is x equals to 0. Okay. So this is 1, this is 2, 3. So every point in x, now there is an observer, and what they have a clock, and they have all these clocks are synchronized, and they have the paper. Okay. Now flash is going past. At some point t, so this is flash is going this way in x. At some point he was here at the position of the observer -3. So when the observer in for whom -3 is written in his paper, when he sees flash and he sees flash just passing by him, maybe they clap their hand together as they go by. So 3 claps their hand, 3 writes down the time. So -3 is written on his top, and then he writes down the time here. So maybe he writes down a time 2. Just a number I'm writing down. And he goes by. So when he goes to from -3 to plus -2, again claps with the person at -2, -2, he writes down another time. Okay, so this way it keeps on happening. So all these people, because flash is going from the left to right, he will encounter all the people, they will all clap hand with him and write down the time when the clap happens in their page. And now what they will do, so that is, so we have third step in our measurement process. In the fourth step in the measurement process, flash has gone by, so they have done their job, so they come back to the same cafe, if you wish, where they started from, and they compare their measurements. So what we will know now? So you will know that, okay, flash was at, x of flash was -3. So let me call this 1. x1 was -3 when t1 was 2. x2 was -2 when t2 was 3. And all the papers are at the same place. Now they can compare. And when they compare, they can figure out what is the velocity of flash. In this case, v will be 1 unit. Right? -2 minus -3 by 3 minus 2 is 1. So that is how they will be able to measure the velocity of flash. There is one very important thing here. This measurement is not done by one person, but many people. You need at least 2 people if flash is moving at a constant velocity. Then in between any 2 people, the velocity will be same. So if we consider that case, I need at least 2 people measuring the velocity of the flash. For doing any such measurements, where 2 spatial points are involved, so like for example, we compared these 2 spatial points. At one case the x's value is -3, other case the x value is -2. Only one person cannot do that measurement. 2 people has to be involved, and that is a very crucial point. Whenever I want to do measurements at different points in space, those measurements are to be done by different observers. A single observer cannot do those measurements. Okay. So this is the measurement process, which now essentially mean if I want to constitute a reference frame, I need infinite number of these observers, and each observer is sitting, is not doing anything, just sitting over there. They cannot move from their position. Whatever is written on the top, the position is written on the top of his uh, small page. He has to be there at that position all the time, cannot move out of it. Okay, so that is how, using infinite observers, we constitute one reference frame. Okay, so that's the constitution of reference frame. Now, to understand all these things happening, we used this as the trajectory of flash, right? So this is how flash was moving. But you see, it's not very good, because the trajectory is not very good because it doesn't give us a feel of where flash was at which time. We just know that he's gone through these values of x. So we want to describe such trajectories diagrammatically. So we want to draw diagrams, and you'll see again it helps us understand things in special relativity a lot. And these will have space and time both. So these are called space-time diagrams. So what is a space-time diagram? So let us start with a few examples. So in this case, so just like the previous case, we draw the space, and again I'm sticking to only one axis. It can be done in with all three, but it is complicated and it's not possible to draw, of course, in a two-dimensional board like this. And the y I plot c times the time, just to make the dimensions equal. You could have plotted time also, but this makes the dimension equal. So this, anything that I plot in this is called a space-time diagram. Like for example, I can plot an event. I call say E, just like we were discussing earlier. An event E can be something happening at the time t1 at the position x1. So that's a point here in the space-time diagram. E, say E1. I can have something else happening at some other time, some other position, E2. These two actually can be these two events. So this is E1, right? And this is E2. I can call these E1 and E2. So this is one position of flash, the E2 is the other position of flash. So flash also moves in between these two positions. So which means we should be able to figure out what is the trajectory that flash follows. Well, if I write E2 here, we'll see something interesting, more geometrical about this diagram shortly. Obviously, flash has gone from E1 to E2, so I don't join this line, extend it here, and ask the question. So let me encircle these 2 points. What is this angle, theta, if we call it theta? You see, we'll agree that the velocity of flash is x2 minus x1 by t2 minus t1, is by definition, is what we call the velocity. If I divide this by c, I get this. But just from geometry, this much is ct2 minus ct1, and this much is x2 minus x1. So x2, sorry, c t2 minus t1, which is the difference in y direction, here, divided by x2 minus x1, which is the difference in x direction. What do I call it? That is the tan of theta, tan of this angle, right? That you have learned in your plus 2. in the in coordinate geometry, and that is essentially v by c that we have just. I'm sorry, it's not v by c; it's c by v. C by v. So we have learned that this angle theta will be tan inverse c by v. So what is the angle theta? Angle theta is kind of the trajectory of flash, trajectory of somebody moving with a velocity v. Let us look at it a little bit closely. Let's say that, okay, so fine, so this we see from this diagrammatically. But say flash is moving and its position as a function of time is xt, x as a function of time, as a constant velocity. So you will agree that this is how he moves. Xt will be x naught, which is the position at t equals to 0, plus that constant velocity times time. Now, if I want to draw this x as a function of t in my space-time diagram, I'm sorry, this y is not y, it's essentially c times t, right? How will it look like? Well, at t equals to 0, remember that this line is t equals to 0 at all x. That is what I mean by this x-axis, right? This line x equals to 0 at all t. All time x equals to 0 at that line. And if I draw lines which are parallel to this line, what doesn't change along these lines? Along these lines, time doesn't change. Which means if I consider one event happening here, another event happening here, they're happening at the same time. So we call them simultaneous. Similarly, I have lines which are parallel to the CT axis. Along this line, x doesn't change, right? Or space doesn't change. So a flash at t equals to 0, so t equals to 0 is everywhere in the x-axis. So let's say at this point is x0. So x equals to x0 at this point. So that is where flash was at t equals to 0. And he has a velocity vt, so his v is say positive. So his position in x is increasing. And it's increasing at a constant rate because v is constant. So you can see that he will follow a trajectory like this. So that is exactly what we saw the last time also. This is the same thing that I am drawing over there. Now we have got from a more general relation. Such trajectories in the space-time diagram are called world lines. It's just a name, but they are called world lines. Okay. And let us try to draw a few such trajectories. And that's where we will end our discussion today. Okay. So let us try to draw a few such trajectories. Some examples. Examples of world lines. First example is particle or a person moving with, this is what exactly we have done just now, constant positive velocity. This is just the example of flash. Okay. If you are listening, you try to do this, start trying doing this yourself. So particle at rest at x equals to x naught, say. There are two cases. Third case is, say, particle moving with constant negative velocity. Light moving along positive x direction or negative x direction. Okay, so let's try to draw these four of these. And so this is x, and let me draw t from the middle. So most of the times you will see we will draw only the first quadrants of the space-time diagram, and just I will keep for the time being at least hint of all the four quadrants. There's this line goes a little bit down also, so you can see. Okay, let's first write the first two. Particle moving with a constant positive velocity. This we have just seen. This is the case here. Particle moving with a constant positive velocity. So this will be, it will be at some x naught here, and then okay, straight line. This angle theta, and remember that tan theta is c by phi. Particle at rest. If it is at rest, then the v is 0, right? V is 0, then the only way you can have that is like c by 0. So theta has to be pi by 2. The particle at rest, you can imagine. So the particle at rest, it was at x equals to x0. It's at rest, it's not moving. It's always be at x equals to x0. So that will be a line for parallel to the CT axis. My drawing is not as good, but that is what you will get, right? So these are just like these lines. These lines. They are like particles at rest. All our observers will have this type of trajectories, because remember that they sit at a given position, and so they always remain at rest along these trajectories. So when I talk about measurement, it is essentially when I'm measuring the position of flash here, the clapping of flash and that observer is happening at that point, happening with the observer which is sitting in this line. And then when the other measurements is happening here, say, the clapping is with the observer who is sitting in this line. Two different observers where the world lines intersects, the measurements happen. Okay. So what happened when I say the particle moving with a constant negative velocity? So let me draw this space-time diagram once. Well, its x will decrease. So instead of a slope, instead of a line with a slope in the right side, this line will be like this. And now the interesting bit, what happens for the light? So say at t equals to 0, I send out two light beams. One is at positive x, another is that towards negative x direction. So I send it out from here at t equals to 0. I start sending the light beams from here. The one which is in positive x direction will always move in the speed of light. So v for that is c. So tan theta is c by c is 1. So here tan theta is 1 for light, which means that theta is 45 degrees. So light, I will draw always light like this wiggly lines, because it's representing the wavy nature of the light. It will go this way. So always 45 degrees. And you see that 45 degrees are like in between the x-axis and the ct axis. Okay. So these are the space-time diagrams which we learned today. So we have gone a little bit off the topic, you may think, but you will see this will come of enormous use when we will start using the postulates of special relativity starting from the next class. Thank you. That's it for today.